Okay, so we've taken a look at translational and rotational kinetic energy. Now let's take a look at the work and energy theorem. This is all still going to apply, except that we need to add another definition to work, and that's right here. This is rotational work, if you will. Keep in mind that we've already looked at work as being the integral of F dot dr. But what's rotational force? Well, rotational force is moment, and rotational position is angle. And so when we do an integral of m dot d theta, and really I don't even need to give it a dot product, m d theta, then that's also another form of work. And so if there's a moment that's causing something to rotate, and we've seen this already in the past, but if there's a moment causing something to rotate, then we can integrate that moment as a function of theta. That'll give us the work done by that moment. So the work and energy theorem is the same. The change in kinetic energy, which is the new kinetic energy minus the old kinetic energy, that's going to equal the work done, and that could be a combination of forces and moments. There might just be forces, there might just be moments, but there might be both. And so if both of them exist, then we add in all of the forces and all of the moments integrated over their respective positions. In a similar fashion, we've already defined power. Power is the derivative of work with respect to time by definition, hence the 3 bars on my equal sign. And in the past we found out that that was force times velocity. We might consider that to be translational power. So rotational power will be rotational force, but that's just moment, and rotational velocity, which is omega instead of v. Same equation, just put in the rotational terms instead of the translational terms. So moment times angular velocity will give me the rotational portion of the power. And again, there could be translational and rotational power involved. So let's take a look at an example here. I have a 500-pound flywheel, and it starts off at rest. So a flywheel is just some rotating object, usually a ring of some type. And I'm given that mg is equal to 500 pounds. And it starts from rest, so the initial omega is equal to 0. And at that point, a constant 200 pound-foot couple is applied. So there's a moment now equal to 200 pound-feet. And I could also say foot-pounds and be completely legal. And then it executes 750 revolutions, so delta theta is equal to 750 revolutions. But I generally don't want to use revolutions. I want to stick with radians. And so that's 1500 pi radians. Because remember, each revolution is 2 pi radians. At the end of that time, the flywheel has reached a speed of 3,000 RPMs. So omega 2 is equal to 3,000 rotations per minute. That's 6,000 pi radians per 60 seconds, which is 100 pi radians per second. At that point, the couple is removed, and so the object is just going to spin, except it is going to slow down because there's a couple with a magnitude of 12.5 pound-feet that's causing it to slow down, and that's due to friction. So that friction will also be there when it's speeding up. So we're interested in the radius of gyration of the flywheel, and that's going to come from the moment of inertia, which we'll get to in just a moment, and the number of revolutions that the flywheel executes after the couple is removed before it comes back to rest again. Because remember, once we've gotten it up to 100 pi radians per second, it's going to slow down until it finally stops. Okay, well, the initial kinetic energy is equal to 0. Then we apply the couple over a certain amount of distance, in this case angular distance. So I have T1 plus m d theta, but keep in mind when I integrate this, the moment is constant. So this will just be T1 plus the moment times delta theta, and that's going to equal the final kinetic energy. And I'll do this until the very end of its rotation. And then I'll do this all again during the slowdown process. So I'll apply this formula for the speed up process, and then I'll apply it again for the slowdown process. So the initial kinetic energy is 0. It's all rotational. There's no translation here. So I end up with the moment, which is 200 pound-feet, but I'm going to go ahead and subtract the 12.5 pound-feet for friction. So 200 pound-feet minus 12.5 pound-feet, accounting for friction. And that takes place over an angle 1500 pi radians. Now again, radians is dimensionless, And so when I'm done with all of this on the left-hand side, I'm just going to have pound-feet. I'm not even going to worry about radians as far as units go. So this is 187.5 pound-feet times 1500 pi radians. And that's all equal to 883,573 pound-feet. And since that's the kinetic energy then after that process has taken place, I can set that equal to 1/2 I omega squared. But omega is 100 pi radians per second. I'm going to square that. And so if I solve this for I get 17.9, and that's going to be slug feet squared. And then I'm going to set that equal to mk squared. But keep in mind the mass is 500 pounds divided by gravity. So the mass is equal to 15.53 slugs. That should be a k squared. And so my radius of gyration k will be 1.074 feet. Okay, so my energy then is 883,573 pound-feet. So that's my kinetic energy, and that's equal to T2. Now I'm going to go through the slowdown process. So I take 883,573 pound-feet, and I'm going to slow it down so that's plus a negative 12.5 pound-feet. That's the frictional moment, times delta theta, which is what I'm looking for. And that will equal T3, but I'm slowing down till I stop. And so T3 is equal to 0. And so delta theta is equal to 70,686. And there's no units there, so that's radians. And that'll turn out to be 11,250 revolutions. Okay, let's do one more example. This one's got a lot of things going on. It's really kind of an interesting example. So I've got this double pulley system, which we kind of looked at already. And it's attached to two blocks. There's block A, which has at 11.5 kilograms, and block B at 9 kilograms. And then the double pulley system itself has a mass, I'll call it m sub p, of 14 kilograms. And the centroidal radius of gyration of 165 millimeters, which is 0.165 meters. Okay, the system is released from rest. And so if it's released from rest, then omega 1 is equal to 0. V sub 1a is equal to 0, and V sub 1b is equal to 0. So the total kinetic energy in the beginning, T1, that'll be equal to 0. But block A is going to fall, and so gravity is going to be doing work on block A. And so the work due to gravity is just equal to m sub a g times delta y. And we're given in the problem here that delta y is equal to 0.9 meters. The object is falling, so the delta y is down, mg is down, and so the work here will be positive. But there's also going to be work due to friction between block B and the surface. Now in this example, the normal force is up, gravity is down, and the tension's to the left, and so the normal force is equal to mg. And so the force of gravity, and this will be kinetic friction, is equal to 0.25 times the normal force, which is mg. And that's also going to do work, but now the frictional force is to the left, and this object is being pulled to the right. And so this is going to be minus the force due to friction times delta x. But one thing of interest is delta y and delta x. They're definitely related because of the way this pulley is set up. So notice this is being pulled down to distance delta y, and that's attached to the pulley at a radius of 250 millimeters. So delta y divided by 250 millimeters, or 0.25 meters, that's going to equal the delta theta through which the pulley rotates during the falling process. But that's also going to equal delta x divided by its radius, because it's wrapped around right here at a radius of 0.15 meters. And so this equation will give me a relationship between delta y and delta x. So work and energy tells me the initial kinetic energy, T1, but that's equal to 0, plus the work done by these two forces, that's going to be 11.5 kilograms, times 9.8 meters per second squared, times 0.9 meters, that's the work done by gravity, minus 9 kilograms, times 9.8 meters per second squared, that's the normal force, times 0.25, that's the coefficient of kinetic friction, times delta x. But according to this equation here, delta x will be 0.54 meters. And so we put in 0.54 meters here, and that will give me the work done by my external forces. And if I did all that correctly, I get 89.523 joules. And again, I use 9.8 instead of 9.81, so if you calculate that with 9.81, you'll get a slightly different answer. Now this is going to equal my total kinetic energies. Well, that's going to be 1/2 11.5 kilograms times the velocity of A squared plus 1/2 9 kilograms times the velocity of B squared. And keep in mind this same relationship here that I had between delta y and delta x is also going to be the relationship between V sub A and V sub B. So delta y over delta t, all divided by 0.25 meters, that's going to equal delta x over delta t. In other words, all I've done is I've divided both sides by delta t, divided by 0.15 meters. Well, this is just V sub A over 0.25 meters, and this is just V sub B over 0.15 meters. And so V sub B equals 0.15 meters over 0.25 meters times V sub A. And so I'll use that for substitution. But I need to also add in 1/2 I of the pulley times omega of the pulley squared. And keep in mind omega of the pulley will equal either of these velocities divided by their respective radii. So here's the velocity of A. So let's just say that that's going to equal the velocity of A divided by 0.25 meters. So 89.523 joules equals 1/2 11.5 kilograms times the velocity of A squared plus 1/2 9 kilograms times the velocity of B, but that's 3/5 the velocity of A. Square that, right? This is equal to 3/5 the velocity of A plus 1/2 I, but I is 14 kilograms times 0.165 meters. Square that. And then omega is V sub A over 0.25 meters, and square that. And so my right hand side becomes 10.42 kilograms times V sub A squared. And so I get V sub A equals 2.93 meters per second. And then I could solve for V sub B using this equation and omega using this equation. Now once A has hit the floor, there's no longer a force pulling on the pulley, but the body in motion will remain in motion. And so the interesting thing is at this point in time, there is a kinetic energy. And so to answer the second part of this question, we take the kinetic energy, which is 1/2 I omega squared plus 1/2 m sub b v sub b squared. That's the existing kinetic energy. And we're waiting until everything comes to rest. And so we'll subtract the frictional force times delta x, and that will equal the final kinetic energy, which I'll label T3. That will be 0. So I have 1/2 14 kilograms times 0.165 meters squared times omega, but that was V sub A, so that's 2.93 meters divided by 0.25 meters. I'm going to square that, plus 1/2 9 kilograms times 3/5 V sub A, which is 2.93, that should be meters per second, squared, minus 9 kilograms, 9.8 meters per second squared, minus 9 kilograms, 9.8 meters per second squared, times 0.25, that's the force due to friction, times delta x, the distance it travels after block A has hit the ground. And in the end, this will all equal 0 because I'm going to slow down until I stop. And these first two terms will be 40.12 joules minus 22.05 newtons times delta x. And so delta x equals 40.12 joules over 22.05 newtons. Remember, a joule is a Newton meter, so this will have units of meters, and I get 1.82 meters. So that's how far it travels before the frictional force of block B slows down block B and the flywheel. And if I wanted to know how much rotation does that go through, keep in mind the 1.82 meters is wrapped around 0.15 meters. So delta theta would be 1.82 meters over 0.15 meters, because V is equal to R omega, or X is equal to R theta, and I get 12.13 radians, which is 1.93 revolutions. And that's just for slowing down. That doesn't include the speeding up process. We would have to take 0.9 meters, which is how far that block A fell, divide that by 0.25 meters, and that would be 3.6 radians. We add that to this for the total amount of delta theta that the wheel would have gone through.